Image Sandia National Laboratories researchers Giulio Borghesi, left Jackie Chen, center, and Alex Chrisman discuss a flame simulation. View more credit. Dino Vernas, Livermore, California. A cool flame may sound contradictory, but it's an important element of diesel combustion, one that, once properly understood, could enable better engine designs with higher efficiency and fewer emissions. Sandia National Laboratories mechanical engineer Jackie Chen and colleagues Alex Chrisman and Giulio Borghesi recently identified novel behavior of a key, temperature-dependent feature of the ignition process called a cool flame in the fuel dimethyl ether. The adjective cool is relative. The cool flame burns at less than 1150 degrees Kelvin, 1610 degrees Fahrenheit, about half the typical flame burning temperature of 2200 degrees Kelvin. While cool flames were first observed in the early 1800s, their properties and usefulness for diesel engine design have only recently been investigated. We're trying to quantify the influence of cool flames in stratified turbulent jets during the ignition and flame stabilization processes. The insights gleaned will contribute to more efficient, cleaner burning engines, Chen said. Our holy grail is to understand the physics of turbulent mixing coupled with high-pressure ignition chemistry, to aid in developing predictive computational fluid dynamics models that can be used to optimize engine design. The team's research has shown that during auto-ignition, the spontaneous ignition of injected fuel in a combustion engine, cool flames accelerate the formation of ignition kernels, tiny localized sites of high temperature that seed a fully burning flame in fuelian regions. The work was performed at Sandia's combustion research facility using direct numerical simulations, a powerful numerical experiment that resolves all turbulence scales, and was published in the Proceedings of the Combustion Institute with Chrisman as the lead author. The work was supported by the Department of Energy's DOE's Office of Basic Energy Sciences. Borghesi further extended the cool flame study by performing a three-dimensional study on endodecane, a diesel surrogate fuel that has been the recent focus of Sandia's engine combustion network on spray combustion in diesels. The study that Chrisman authored with dimethyl ether, a simpler fuel, was in 2 dimensions. Borghesi's paper is pending publication. Taken together, both Chrisman's and Borghesi's papers will form a comprehensive study of low-temperature chemistry in autoignitive flames at different stages of ignition. Cool flames can improve engine design. The details of starting an engine are often taken for granted. Unlike a gasoline engine, in which the fuel-air mixture is ignited with a spark plug, in a diesel engine the fuel must auto-ignite when it is injected into the hot, compressed air that is in the piston at the top of the piston stroke. As the fuel is injected into the engine cylinder, rapid mixing and combustion combine to burn the fuel and drive the engine. While this lasts mere fractions of a second, the conditions of the flame that start this powerful process are crucial for improving engine efficiency and minimizing pollution formation. The cool flame studies were performed at the DOE's Oak Ridge Leadership Computing Facility on Titan, a 27 petaflop supercomputer, using a computational grant from DOE Insight, or Innovative and Novel Computational Impact on Theory and Experiment. Computations using some of the world's largest supercomputers, such as Titan, are required to produce an accurate and detailed calculation of the autoignition process. Combustion processes are challenging to study because the fuel itself is quite complicated, Borghesi said. Fuel oxidation chemistry consists of hundreds of species and thousands of chemical reactions. The realistic simulation of diesel combustion needs to capture this complex chemistry accurately in an overall model that includes turbulent mixing and heat transfer. As part of the DOE Exascale computing program, the team collaborates with outside institutions including NVIDIA, Lawrence Berkeley, Oak Ridge, Argonne and Los Alamos National Laboratories, the National Renewable Energy Laboratory and Stanford University to develop performance-portable algorithms to enhance the computing efficiency for direct numerical simulation combustion studies. Team focus turns to speed, structure of flames in diesel engines. In the future, the team would like to investigate basic questions about the speed and structure of flames at diesel engine conditions and study the relationship between spray evaporation, ignition, mixing and such processes associated with multi-component fuels. These basic questions will contribute to studying the cool flame's crucial role in engine energy production and exercise the valuable capabilities of direct numerical simulations running on exascale supercomputers as a highly precise and detailed numerical simulation method. Sandia National Laboratories is a multi-mission laboratory operated by National Technology and Engineering Solutions of Sandia LLC, a wholly owned subsidiary of Honeywell International Inc., for the U.S. Department of Energy's National Nuclear Security Administration. Sandia Labs has major research and development responsibilities in nuclear deterrence, global security, defense, energy technologies and economic competitiveness, with main facilities in Albuquerque, New Mexico, and Livermore, California. Disclaimer: AAAS and Eureka Alert are not responsible for the accuracy of news releases posted to Eureka Alert by contributing institutions or for the use of any information through the Eureka Alert system.